So given that this is SciPy, I actually kind of talk more on the code side, and this was one of the first ones I'm doing on the code side, less on the material side, but I'm touching on some of the material stuff. If you're interested in that, I could probably give you whole other talks on all that stuff too, so just let me know. The Potentials repository itself is a website hosted at NIST, and if you go on the web page, you can see it pops up this phase diagram. You can click on a given element or a set of elements, and it gives you a list of all the interatomic potentials that we have. The potentials that we have in here in this database, they tend to be focused on crystalline materials. So you have metals and ceramics as the large focus. When you click on chromium, you get the list of all the different potentials. There's a unique ID for each potential, citation information about what the original usage was for that interatomic potential, which other potentials in the repository actually share sort of the same type of interactions, and then links to download the parameter files. On top of that, there's a C-computed properties link for each version of every potential we have that is LAMMPS compatible. That if you click on that, then it pops up a separate web page with a whole list of crystalline and crystal defect property calculations that have been evaluated for all those different interatomic potentials. The importance of this is that all these interatomic potentials that we host are empirically fit. They're fit, trained, whatever you want to call it, to specific properties of interest to the original developers. So if you go to something that was not in the original sort of training fitting set, then you're not guaranteed to get good results at all, and so we need a means of sort of evaluating which potentials are likely the best for individual use cases that may be of interest to people in the community. To support this infrastructure, there's kind of been 6 different Python packages that have been implemented related to all this. This talk's going to go very briefly over the ones that don't have stars, just to give you kind of a feel for everything, but then the 2 with the stars are the ones that are kind of the focus of this talk in developing kind of that user-friendly API type design. So starting from the very bottom up, the database itself is based on JSON XML equivalent data models. So it's these data models, this information that can be represented in equivalently JSON and XML. We pick the tree-like data structures in large part because of the modular design, that you can think of the data itself as being object-oriented. So the sub-elements in the records can represent different sort of sub-elements of the different, and then you can compose the full schemas by basically just piecing together the big blocks. Having it being JSON and XML equivalent means that you can take advantage of the tools and features of both JSON and XML while imposing relatively few sort of limitations on how you can design your schema. Then to help that, the first Python package was data model dict, which just takes a Python dictionary, or I guess it was ordered dict since it was designed a long time ago, and adds JSON XML converters to it. So on the left-hand side, you can build your tree-like data structure as just a dictionary or embedded dictionaries. And then on the right-hand side, in a single line, you can save those as JSON or XML strings. The class itself has a few extra little features in there, such as you can do some sort of simple iterative down-the-path tree-line searches to find elements that you are looking for. And you can either return the value that is found out there or the path to that value, so that then allows you to kind of do more kind of complex searching and exploration. And the top left stuff is just that there's a few extra functions that it's basically with the XML records, it's a little bit ambiguous when you go to JSON or Python if certain entries can be single values or multi-values, because XML doesn't really differentiate between the two. And so there's just functions where you can treat sub-elements as lists even if they are not lists. And so you got a kind of an append and as list methods. Simple stuff, okay. Then that's the data. We talk about the database that we have under the hood, and we use a configurable data curation system, or a CDCS database. The link on the left is to the CDCS project page, so if you want to know more about this type of database, you can go there. The link on the right is to the specific CDCS instance that is used by the Potentials repository. The kind of the original intent behind the CDCS database is that it was meant to be serve as a nice tool for like material scientists to enter data. So you can go to the web landing page for every single database. You can explore the data there. You can, if you are say doing an experiment, you can manually enter data into the schema and then click save, as opposed to say writing it in a paper notebook and then transferring it later. In addition to that, once the data is in the database, it's saved as XML, which in the web landing page means that you can automatically be transformed into pretty HTML and other data formats using XSLT transformations. Then behind the hood, every single CDCS database also has REST API calls, so you don't have to just go through the web landing page. You can do everything sort of really fastly in mass, and part of the Interatomic Potentials Repository project, I ended up developing the CDCS Python package that then interfaces with the REST APIs for the CDCS databases. It's a lot of CDCSs. So the gist is it's fairly simple, and the idea is that you have a REST client that just, when you initialize the object, it saves your URL to your database, it saves your password authentication stuff, and so whenever you do a REST API call to any REST database, you just need the relative link and the whatever parameters you're interacting with. So it's just a simple, fun little feature. And then the CDCS one adds on to that by adding additional methods that are specific to the CDCS REST API calls. And so in the bottom here, I have a query, I have a curator instance. I'm doing a query to a template schema potential. I'm giving a keyword value. It does all the REST API stuff for you and returns the results as a pandas data frame. Now, an interesting part about this is the framework that we designed for the potentials repository, but ideally at the end of the day, the user should not have to care what the data structure is, what the database is that they're interacting with. And that's kind of where this idea of the Yabba Dabba for Gay-a-based database came from. And the idea is that it's make it easier for the people who are generating data and developing packages to support that data to easily release these user-friendly packages. So in fancy terms, it's a mid-level abstraction layer for data and database interactions. More specifically, we're supposed to allow the developers, data generators, to design code to support their data rather than worrying about the database infrastructure, and allow users to access the data without needing to be database experts themselves. And it does that sort of by generalizing the idea of what a database is and the idea of what a record is. For the databases, you have a base database that just has sort of common interaction methods for different types of databases. So you have get, add, update, delete records. You can also get the information back both in sort of the object form as well as a pandas representation. And you can also interact with sort of tars and then do kind of higher level things like copying all records from one database to another. And then the idea then is you have the subclasses of that, which handle how you do those specific functions to different types of infrastructure. So the local database uses the data model dict and pandas to interface with just local folders of JSON and XML files and CSV metadata cache files. Mongo uses PyMongo to interface with MongoDB, and the CDCS uses the CDS package. And in case you're wondering, you don't have to use the generic ones, but if you do, because you can always access the underlying interfaces, but if you use the generic common methods, then it actually does not matter to the end user what infrastructure where your data is actually stored. So the trick then is for the developers, you just have to define record classes for each schema that is in your database. And so in short, most of the kind of the attributes and methods I'm listing here are pretty much you have the information in that data model, so the JSON XML format. You want to interpret that into your attributes of a Python object, so you just have to convert back and forth, add converters back and forth between the two. And then once you do that, the large focus then is just what do you want the end users to do with the data in that record, and what values you want them to access, and what operations you want them to do. One thing to point out here is this queries dict. So then the attribute booster says queries dict, which is a dict of query objects. So this is kind of a little bit of the magic that's going on in some of the tricky things, because when I'm talking about the generalizing the database idea, you want to be able to do queries to the databases, but the best way to perform those queries depends on your database infrastructure. So the idea for these queries, and then is the kind of the middle left, you see the database, get records, then you give it the name of the schema you want, and then below that I have key equals some value. So that key is a keyword argument that is recognized by the potentials record format, and so you go into in the code, it goes to this queries thing, says, okay, the key value is associated with some query of string match, so it knows to perform an operation to check the database for exact matches of the string that was given in the function to the database records. And then the name and the path simply just tell it, the code, where to find that value in the different types of databases. And then at the end of the day, you have the description field that allows users to, on the bottom right-hand side, generate the nice kind of doc description of what all the keyword arguments that are supported by that specific record style for that schema, yeah, whatever. So a quick view of this in operation, in action. I've been doing a lot of liquid calculations recently, which is kind of a new thing for me, and doing radial distribution function calculations. It was enough different from my other stuff on sort of the solid crystallines that for the time being, I decided I don't want it mixed in with my other calculations. So with Yabba Dabba, I just quickly spun up a prototype package in database, where the database is just a folder of JSON files on this laptop right here before you. And by defining that record class for that specific type of data, I already have all the database interaction stuff. And so you can see that I can do a search based on elements and temperatures. I get all the matching results and can just nice and easily plot the information without needing to know what the JSON file looks like. And the idea then is that once I'm ready to release this data, this prototype thing, all I have to do is pick which externally accessible database I want, whether it's Mongo, CDCS. I upload, copy the records over there, and I release my Python package, and it's done. That's it. Everything's out there. It's already a nice database, nice interface. Then the advanced version of that, the next package in the kind of the list is the potentials Python package. So this has the Yabba Dabba based records that provide APIs that are specific to the records that are stored in that potentials.dist.gov CDCS database. So it makes it possible for users to explore and download all the Interatomic potentials and the associated metadata content that is stored in the repository. So individuals can actually, if they wish, create their own local copy of the NIST Interatomic potentials repository and run everything offline, or they can do the remote interactions with the CDCS database. And then there's a whole bunch of just kind of, right, and so the idea is you can do everything in Python, or at least on the right-hand side here in a Jupyter notebook, you can use these Jupyter widgets to do your own kind of personal query searches for different matching Interatomic potentials, and it displays in the nice pretty HTML exactly as it appears on the repository website. And there's a bunch of extra kind of features and tools in there for people who care about this type of data and everything. I'm going to skip that one. It's just so going on, moving up the line of what we need to do for the atomistic calculations, we have the Interatomic potentials. Now we need the configurations. And so this is where the Atoman package comes in. So Atomistic Manipulation Toolkit. It's designed to allow users to load, build, and manipulate the atomic systems with a focus on kind of the relatively large-scale complex systems that you typically see with classical potentials versus the sort of the small-scale ideal cell stuff that you get with DFT. And a large focus is on being able to create crystal defect configurations and analyze them with some built-in features allowing you to run and wrap around LAMP simulations. Since this is talking about the database API stuff, where does Atoman fit into this? Well, the Yabba Dabba record stuff is entirely modular, and so Atoman inherits all of the record classes that were defined by the potentials package. So if you want to use both the structure and the potentials, you can use AtomMan, and it already gives you all the access to all the stuff that was in potentials. And then on top of that, because we're now allowing for atomic configurations, you can define additional record classes for those atomic configurations, as well as record classes that provide parameter sets for generating defect configurations with those. So the right-hand side here, you can kind of see some code. The idea is that before this, you've already queried and fetched whatever interatomic potential you want, and then you just do load a relaxed crystal that has been relaxed with that specific interatomic potential. I could, of course, give it more limitations to be more specific, but I didn't here. And when it does that, it spits out a list of 8 relaxed crystal structures that have been relaxed specifically with that interatomic potential. The number 1 is the most favored one. I select that, it gives me the unit cell, and from there, then I can easily manipulate it and rotate it and generate supercells and everything like that. And with a supercell, then you can do fun stuff like define a cylinder in space, delete all the atoms outside of it, and boom, you've instantly got a nanowire. We're talking about the crystal defects. Another example is this idea of computing your stacking fault energy map. As material scientists, we like to think of it in terms of you pick your crystal, you pick the plane that you want to calculate the stacking fault map for. So that's the first 2 lines of the code on the left. You get your crystal structure, you pick the plane. Then the next set is creating the stacking fault object and simply saying how big of a system do you want it to be. And then the last 2 lines of code are saying how many iterative steps do you want to do to shear the crystal along that stacking fault plane. So I'm doing 30 by 30, and then that's generating all those different atomic configurations for you. Once you have those configurations for you, you run LAMPS or whatever you want, or DFT, to evaluate the energies, and then once you have those, you can give them back into AtomMan with the gamma surface object that takes all of that information, it interpolates between it, and allows you to create the nice pretty 2D or 1D plots of the energy maps. Right, and as I mentioned before, it also has sort of built-in features that allow you to run LAMP simulations around it. The idea, the construction of this is that you write a template LAMP script, and then in Python, you just define the dictionary of terms that you want to replace, fill into the template script. So you can make the potential, your system, whatever variable. It generates a LAMP script, you run it, and all of the resulting thermal information is automatically read in and converted into pandas data frames for you. So it's nice and easy to plot after that. What this allows essentially with AtomMan is you can design single Python scripts that allow you to run and develop and design calculations. So with AtomMan, it makes it possible to design those property calculations that I mentioned way back at the beginning. And so the final component, the final package of this kind of whole stack is the IPRPy calculation framework. And so what it does is it collects those complete property calculation scripts that are used by the NIST Interatomic Potentials repository for evaluating the properties of the different interatomic potentials. And the large focus of this project, what has kind of been in mind since the very beginning, is can we make the calculation methods themselves as well as the resulting data accessible at all levels you could possibly think of. So all the way from sort of maybe the basic end user who trusts that I know what I'm doing, who just simply wants to click go and compute the properties, all the way down to, say, maybe the advanced researcher who wants to double check that I'm doing everything correctly. And so it's a lot of work has gone into this. It's easily installable with pip or conda. You can run in Python command line. It's all open source code. There's a modular handling of the calculations, and there's a whole bunch of extra stuff for kind of doing workflow operations and designing high throughput workflow processes, which if you want know more about how that AtomMan or IPRPy does that, talk to me afterwards because I didn't have too much time here. And then on the right-hand side is the list of the 24 different calculations that are currently part of this framework. And so, so one last kind of boring slide here is to implement your calculations into the framework. The idea is that every single calculation is just a Python function. And because of that, this is not limited to just atomistics. You can make your Python function do whatever you want. And as long as it takes normal Python values and objects as inputs and returns a dictionary of output values. I picked dictionary just because I wanted to know what the outputs are and not have to worry about the order of tuples and everything like that. Then the idea is that to implement those calculation functions into the framework, you define a calculation class that links that function to the framework. And some of the magic here of getting back to, well, making the data accessible is that every single base calculation class inherits from Yabba Dabba record. So all the calculation objects are record objects. So you already have the framework, the setup for doing those database interactions. And then the additional kind of attributes and methods for making it into a calculation is just kind of is focused on the idea of taking sort of basic inputs, preparing your calculation, and then analyzing the results into the nice, pretty stuff, as well as some metadata for the high throughput type calculations. So what does this look like in action? Once you have an implemented calculation, on the left-hand side, you can load a specific calculation, you define your parameters that the calculation needs to run, you run it. Or, on the right-hand side, there's this key value text-based input parameter file that all the calculations have. You just simply fill in the values that you need to, pass it into the calculation object, it runs it, and it's done. When it's done, all the values get automatically saved to that record object so you can instantly plot them as class attributes. Or, since it's a database, or since it's a database record object, you can instantly convert that to JSON or XML, save it, and use it with an external tool. In addition to running from Python, you can also do everything from the command line if you should wish and you are fearful of Python, but I don't think that's anybody here. So the next step, I think, is a very interesting idea that has been kind of throughout this idea, is that everything so far, the calculations have been essentially black box. And while that's kind of useful for basic users, we don't want that. We want transparent box. And the way we've kind of come about doing that is creating Jupyter demonstration notebooks for every single calculation. So in a single file, we've got the nice formatted markdown description of the methodology and theory for the calculation, a copy of the calculation function, and then a working example. So a single shareable file has the description and capabilities of that calculation that you can easily hand out to everybody else. And then finally, everything I mentioned so far was just single runs of the calculation. You want to be able to run them in high throughput. And then the framework sets it up that once your calculations are implemented in there, you can set up either a single calculation to run in high throughput across a wide variety of variables, or even design a high throughput workflow in which the results of one calculation become the inputs for the next calculation, and so on and so forth. And when, at the end of the day, since everything is a Yabba Dabba record, I can just say, get the database, give me all the records for this calculation, and with this specific interatomic potential, gives me 10 results, and I can plot and compare the information right away. And then the final example is doing sort of the same thing, only now I'm doing the calculation for those generalized stacking fault energy maps. I can query the database for looking for results for a specific interatomic potential. It returns the pandas data frame so that I can look through there, pick out the one that I'm interested in, plot, and then the record object has one of those gamma surface objects already embedded into it that has interpreted those results from the calculation, so I can instantly plot the 2D and the 1D plots. And then it's kind of a twist on that is instead of picking a specific potential, I pick a specific stacking fault plane and tell it to get all the results. I got like 400 and some. Then I say, well, okay, that's a lot. Maybe I'll just look at only nickel. And that gives me 48 results. That's still a lot, so I just plot the first 10. And I think this kind of wraps all the way back to kind of the first slides of why we're doing this, that these are 10 results from 10 interatomic potentials that are all nominally for nickel, but you can clearly see that they're giving quite different property predictions for this one type of property. And so with that, I'm just going to end by putting the slide back up of the kind of the names of the 6 projects and their short descriptions.
Thank you, Lucas. Any questions in the room? I see one. Hi, thank you so much for giving that. Can I ask if the Jupyter demonstration notebooks are publicly available somewhere?
Yes, they're all online. They're online and they're also part of the package. So you can either view them online just in GitHub. I think they've also got copies of them on the repository website. You can just go to like the descriptions and see them. So they're, yeah.
Thank you so much.
Yeah.
Yep.
Thank you for a great talk. I'm curious, how well does your code and these methods integrate with other established codes for material science like ASE and PyMatGen? Say if I wanted to take one of your workflows, but instead of using your lamps potentials, I wanted to use an ASE calculator or something like that.
Yeah, so the so AtomMan has a built-in converters between the two methods. So you can do AtomMan system into an ASE atoms or a PyMatGen structure. So, and then if you wanted to say do the IPR Pi calculations, it doesn't care. It doesn't even have to be, like I said, it doesn't even have to be an atomistic calculation. It just has to be a Python function. So it's very adaptable if you want it to be.
But so far, which are the codes that you support out of the box? Is it LAMPS or only, or are there
for
others?
simulations, yeah, LAMPS. Well, technically speaking, when you're doing the atomic configurations, you can pass it to whatever software you want it to. It's just the built-in tools wrap around LAMPS. So yeah, yeah.
Any other questions? Daniel, do we have any questions from the internet? I do also have a couple of questions, so you have a lot more time to think. So one question would be, so far, who has been contributing to this repository? So who's contributing potentials, who's contributing calculations? And a follow-up question would be also, how does this repository differentiate itself versus the OpenKim repository, which does something very similar, at least from the outside?
So the potential submissions are all over the community. I get, I think, consistently at least once a month, one per month. It's been almost closer to probably 2 a month this year. Then for the calculations, it's been predominantly me or grad students so far. For some of the underlying tools in the AtomMan, I'm consistently working with random people just out there. It's like, hey, I'm trying to do this, and so they send me options. When it comes to OpenKim, the thing I'll say right now is that the potentials package and the potentials repository have listings for all the OpenKim models. So if you just go through my tools, you can access both the native lamps and the OpenKim models. And I think that's kind of where the difference is originally, is that the potentials repository was focused on the native lamps parameter files, and the OpenKim was trying to do the fancy kind of API wraps around the potentials so that they can plug into different simulators. So,
I see.
yeah.
Thank you. Any other questions that came up? Doing well? One more question I have is, so since we asked the previous speaker about the materials code support, so I was wondering, so in the end, of course, the focus is on the non-organic materials.
Yeah.
But there are, of course, also organic crystals. So I'm wondering, do you have any potentials that are geared towards more organic systems, and is there any kind of overlap?
I'm trying to remember. I think we've got one meta model for water, and we've got, I think, the original Reacts FF potential. So it's just, I mean, it's whoever submits them, we get whatever they submit. I think the interesting thing would be to see how well, like if you're doing one of the organic crystalline materials, how well stuff like stacking faults and dislocations kind of apply to that. So I don't know. So.
Cheers.
Yep.
But if there are no more questions, let's thank our speaker again.